Hello everyone, myself Aditi. I'm currently pursuing my master's final year in IIT Jodhpur, and my specialization is AI. In the summer break, I'm interning with Socket Labs, and so the topic for today's presentation that we have chosen is bridging linguistic diversity, that is evaluating and advancing AI for Indian languages. So let me get ahead with this. So the first term which when we hear language models is what are language models. So let me start with the very basics. So language models are AI models designed to understand and generate human language by predicting the next word in the sequence based on the context provided by the previous words. Here, there are three main things like scale, adaptability, and contextual understanding. So, scale is they are trained on an enormous data sets capturing diverse linguistic notions. Adaptability is they can be fine tuned for specific tasks like translation, summarization, etc. And contextual understanding, so generation, coherent and contextually appropriate text. Here you can see three examples also of large language models that are GPT-4, Google BERT, and T5 by Google. So moving forward to today's topic, benchmarks. What, why, and how. So what exactly are benchmarks? These are standardized set of tasks or data sets used to evaluate and compare the performance of language models. So this provide consistent and objective measures to assess model performance on various language understanding and generation tasks. Now, why are this important? So I'll mention 4 points. The first one is performance measurement. Second one is the comparative analysis. So they allow for direct comparison between models to identify strength and weaknesses. It helps in the research progress and standardization. So establishing common evaluation criteria, ensuring transparency and reproducibility in the research. The how part, so task specific evaluation, like models are tested on tasks like sentiment analysis, machine translation, question answering, etc. And there are certain metric based scoring like blue score, accuracy, F1 score, etc. Moving ahead to our first benchmark. So first we'll cover all the English language benchmarks and then we'll dive into the Indic benchmarks. So the first one is GLUE, which is General Language Understanding Evaluation. So this benchmark includes 9 different tasks, each targeting a specific language understanding challenge, such as sentiment analysis, textual entailment, and paraphrase detection, etc. As you can see over here, there are this 9 different data sets for these 9 tasks, like COLA, SST2, which is Stanford Sentiment Tree Bank. There is MRPC, which is Microsoft Research Dataset, Semantic Textual Similarity, STS, etc. A small example is like, is this movie review positive, negative, or neutral? This is the task, and the movie review was the movie is funny, smart, visually attentive, and most of all alive. So it assigns a positive score, and the metric which was used was accuracy. For this GLUE benchmark, there were 9 different tasks, and the final score is calculated by aggregating all these individual scores, and hence we get the final score. But even though this is a diverse task data set, there were some limitations. So the first limitation was some tasks may not cover deep understanding of real world complexities. As also this is a static nature dataset, some tasks derived from specific domains like news articles, movie reviews may include some kind of domain related bias. And there were also simplistic tasks, so they might be too simple, like binary sentiment analysis for evaluating the model. So all these issues were overcome by the SuperGLUE benchmark that was launched next. So SuperGLUE is Super General Language Understanding Evaluation. And in SuperGLUE, they were built upon the foundations of GLUE benchmark itself, and there were various other tasks like Boolean questions, choice of plausible alternatives, etc. So the advantages of this were it increased the complexity, introduced more challenging tasks that require deeper understanding. It was a more diverse data set, so benchmarking progress was more better than the GLUE benchmark, and task variety was introduced. So moving ahead, the next benchmark that we are going to see is the HELA-SWAG benchmark. So this benchmark was created using the adversarial filtering. Now, the initial data set included plausible and implausible continuations of scenarios, and models were trained to distinguish between them. And the most challenging one the most challenging examples on which the models perform poorly were retained. This process is known as adversarial filtering. The source material for this adversarial filtering was obtained from ActivityNet Captions, which contains descriptions of activities depicted in videos, and WikiHow, which provides instructions for various tasks. The format for this was each instance in the dataset, as you can see over here, consists of a context, like a sentence or a sequence of sentences followed by multiple choice options. And the task is to select the most plausible continuation from the options provided. So one of the example of this HELASWAG benchmark, a woman is outside with a bucket and a dog. The dog is running and around and trying to avoid a bath. And these are the 4 options. So the correct option has to be chosen among this. Now, like this is one of the common sense benchmark which focuses mainly on the common sense. So the disadvantage with this was, while it is excellent for common sense reasoning, it does not cover the other important aspects of language understanding, such as sentiment analysis or machine translation. This can lead for potential overfitting also, because it might include some bias. So overcoming this challenge, we have the MMLU benchmark. MMLU stands for Massive Multitask Language Understanding. So let's, like, you can see 4 key points over here. So diverse subjects. The scope was here, it covers 57 different subjects ranging from elementary mathematics to professional law exams. Categories included humanities, social sciences, STEM, and other professional domains. And the data set sources were standardized tests like GRE, SATs, APs, professional exams for medical and for law, academic competitions, quizzes, Olympiads, etc. So the issue which we had with the previous benchmark, HELASWAG, which was only based on common sense, here we overcome that we have a variety of other data sets as well. The task types were multi-choice questions, reading comprehensions, and reasoning tasks, and accuracy and etc. were the evaluation metrics. Now, this helped us for real world relevance, as questions are sourced from standardized and professional exams. So reflecting the reasoning and knowledge required in real world, there was multi-domain testing. And this benchmark covers a wide range of subjects and difficulty levels. So the easiness that was provided in the common sense benchmark is also overcome. And in the left side, you can see a picture, the HELASWAG, the linguistic, which is the super glue, and knowledge, which is the MMLU. So as you can observe over here, other models perform well on all range of models, like small models, medium models, large and extra large. But this MMLU benchmark, you can see that small, medium and large GPT-3 model does not perform very well on that. Only extra large model performs above the randomized score. So this tells us that the benchmark is quite diverse in all the notions of it. So now, issues with MMLU. Uh, you can see in this snapshot, this is the leaderboard for MMLU. Now, this is the default style where you have the options A, B, C, D. You have to select one option, and this was the leaderboard. But here the issue is, when like you can change the ABCD into some other notions, so you can see there is a huge drop in rankings. The model which was ranked third directly goes below, phi 2 goes below. Other such issue can be fixed answers, like if the model has learned the sequence of answers, and if we change the sequence, again there is a change in rankings. And close prompt, meaning no options are given and directly model has to answer. So you can observe over here that there is a huge change in leaderboard. So every minute change, such as the order of multiple choice options or the method of answer selection, can significantly alter the model performance. And these variations can lead into inconsistent results, making it difficult to fairly compare all these models. So this highlights the model's reliance on specific patterns rather than the genuine understanding, reducing their robustness. This was one of the major issue with MML. Now we have seen all the English language models and their benchmarks. So now let's go for developing and evaluating LLMs for Indian languages. Now, The first thing, journey of Indic LLMs. So Indic BERT, which was launched in 2020, and Indic BAT, which was launched in 2021. This is where the journey for Indic LLMs started. They focused on natural language understanding and generation, and they were developed with the support from AK Step Foundation. And as you can notice, Indic LLMs is mentioned. It is not given Indian LLMs. Why the term Indic? So the term Indian encompasses more than just multilingual capabilities. We want a model that captures cultural idioms, historical references, regional specifics, and diverse interaction styles. Hence, Indic LLMs was the term which was coined for this. So after Indic BERT and Indic BART, there was adaptation to large open models. So there was a shift in focus. So development of base and chat models were done from open models like Llama, Llama 2, etc. The models which are currently existing is OpenHathi, Airvata, etc., which we are going to see further. This adaptation process had extending tokenizer and embedding layer, continual pre-training using the multilingual corpora, and fine-tuning this base models. So what were the challenges in this Indic language models? So the major challenge was factuality issue. Indic models show good language generation but fall short in the factual accuracy. As you can see in the example above, if someone asks a question in English to ChatGPT, it is answered rightly, but the same question when asked in Hindi gives different results, which are the wrong outputs. So hence translations from these models were okay, but the factual accuracy, the cultural thing which it has to grasp was the issue. And coming to the main question of this slide, why Indic only models are necessary? So there are three main reasons for this. First is the tokenization efficiency. So this English models, the first question which comes is like ChatGPT can translate into Hindi and give answers, etc. So why Indic models? So English models produce up to 4x more tokens for Indic languages, and this and like Indic languages are not efficiently tokenized by English models. This can be a very big issue. Second is the performance on low resource languages. English models perform well on high resource Indian languages like Hindi, etc., which we can see in ChatGPTs, but struggling significantly with low to medium resource languages like Kashmiri, etc., is still an issue, and hence the accuracy gets like fluctuated. So the development of Indic LLMs is crucial for overcoming all these limitations of English only models in handling this cultural diversity of India. So before going to the Indian benchmarks, let me introduce two Indian-based datasets. The first one is the Samanantar dataset. So it is a large-scale parallel corpus collection for Indic languages designed to support machine translation and other natural language processing tasks. It contains 49.7 million sentence pairs between English and 11 Indic languages, and it represents two language families. So here data collection was done from various diverse sources such as news articles, religious texts, government documents, etc. Uh, the process of creation was identifying the parallel sentences collected from English to Hindi at the same time period or related video captions. And there was a scoring function used. So basically, cosine similarity was used on the embeddings to identify the potential translation pairs. And the one having a high threshold was selected, and in the post-processing part, the one which had low threshold were removed and the duplicates were removed. And there was manual validation done, but it was only done on 10,000 sentence pairs across all these 49.7 million sentence pairs. Hence, human annotations was an issue over here. So the issue in this Samanantar dataset, you can clearly see the first one is the table from the paper itself, and the second other two are the screenshots I have taken from this Hugging Face dataset Samanantar. So if you see this example, we call it India, and this is the Marathi translation, आम्ही त्याला भारतात बोलवून घेते. So there is a huge difference in both of these sentences. The first one is saying we call it India, and the second one is saying that we have called a certain person to India. So this is the issue because of the translation. And the second sentence says, he says India is special to him. Here, he and him are pronouns and do not specifically indicate anyone. the translation says विराट म्हणतो की भारत आणि त्याच्यासाठी धोनी खास आहे. So the translation does not at all imply what the sentence was saying, and this can be the potential issue with the translations and everything. And this was the issue with Samananta dataset. So the next dataset that we are going to see is the Sangraha corpus. This is also known as the foundation of Indian LLMs. It is divided into three parts: Sangraha verified, Sangraha synthetic, and Sangraha unverified. So Sangraha verified, this is high quality web content which is manually verified. So it contains around 40 billion tokens, and it is around 22 scheduled Indian languages. And the issue in Samanantar, that there was noise in data, incorrect translations, partial sentences, which could lead to wrong generations, was kind of solved here as we have manual verifications. But still we have the Sangraha synthetic and unverified part. The synthetic part is translations of English knowledge sources to other languages, and this was done to bridge the knowledge gap by translating rich Indian content in other languages. And the unverified part is also high quality content from resources like MadLab 400 or something, but it is unverified. And this was the three parts in which this Sangraha corpus is divided into. So these are the two data sets that we have seen right now for Indian languages. So now focusing our attention on the benchmarks. This is the first Indian language benchmark which was there, INDIGLU. So it is a benchmark designed to evaluate language models on a variety of tasks specific to Indian languages. The tasks you can see over here are like news category classification, named entity recognition, headline prediction, and question answering. So basically, assessing models' ability to answer questions based on given text passages is question answering. Named entity recognition is identifying and classifying proper nouns either in text, etc. So this focused on core NLU tasks. It covered only 11 Indian languages and was primarily used for machine translations and some other data sets. The issue over here was data scarcity, as very limited data of high quality, which was annotated by humans, was available. So this was one of the benchmark. The other benchmark that we are going to see is Indic Extreme. This is one of the comprehensive benchmark for Indian languages, which is currently in a lot of use. It contains the largest monolingual corpora, INDICORP 2. It has around 20 to 21 billion tokens, and it covers 24 languages. So Indic Glue covered only 11 languages from 2 language families. Indic Extreme covers 24 languages from 4 language families. And the tasks over here, there are more tasks than Indic Glue also. There are 9 tasks which are divided as classification, structure prediction, question answering, and retrieval, which have 9 different data sets associated with the same. As you can see in this table, these are the 9 different data sets. So the major advantage over here is the method which you see. Here you can see most of this are human annotated. So we can say that all test sets are either human created or human translated to ensure the high quality and relevance. This is the language part. So in how many languages are these data sets available? So you can see the range from 9 to 18 over here. So the advantages of this over the previous benchmark is human created data. So unlike previous benchmarks that rely heavily on machine translations, Indic Extreme emphasizes human created or human translated data for higher accuracy and cultural relevance. The second is broader language coverage. So evaluates models on a wider range of Indian languages, that is around 20 to 22 languages, ensuring comprehensive coverage. Task diversity includes a wider variety of tasks and enhancing the robustness of the model, and also zero shot focus was included. This is one of the graphs mentioned in this paper. So IndicBERT was trained benchmark on this Indic Extreme, and this is the fertility plots. So fertility plots basically tell you how much tokenization was done. So as we had seen previously, that tokenization is very important for our Indian models as they differ from this English models. So you can see that for the IndicBERT, there is the least amount of this tokenization or fertility score in various languages. These are all the languages that it was calculated for. So this is one other advantage of the same. Okay, moving ahead. Now, as we have seen the Indian benchmarks, and now let's go to the next part, like what are the efforts taken and what are the challenges that we face for this. So there are two ways in translating the data sets. First is we can utilize human translators and native speakers to ensure that translations maintain the integrity and cultural relevance and everything. And the other part is that we can employ translation APIs like IndicTrans 2 from AI for Bharat. This is like the API part is which most of the models are currently doing. But there are various issues which the translations include, like contextual loss. So contextual meanings are often lost, affecting the comprehension and the quality of translations. The partial sentences bit that we saw in the previous slide, that the partial sentences translating them may lead to various ambiguities and incorrect interpretations. Order and format changes also, what we saw in the previous slide. Same applies for the indic part also, that changes in the order of choices or rephrasing the questions might affect the model performance. There was bias introduction in the automated translations because the original data does not contain the bias, but the translations which are incorrect might have some cultural nuances, difficulty in capturing cultural and contextual nuances specific to Indian languages, which is crucial for accurate translation, and resource intensity, of course, because high computational power will be required for all these translations. Um, so as we saw all the challenges, these are two models which are currently the Indian LLM models, OpenHathi model and the Airavata model. They both are developed by AI for Bharat and Sarvam AI. For OpenHathi, the base model was Llama 2, and for Airavata, this was fine-tuned on OpenHathi. The reason for showing this is, in this slide, you can see an example for Airavata model. This is one of the incorrect responses that it gave. On the site, there are various incorrect responses mentioned. So you can see here that it was asked to do an 100 word answer, and it did not give around, it gave around a 50 word answer. There are other incorrect answers present on the site as well. So this shows that basically machine translations are still, the translations that we are doing are still yet to capture the understanding or meaning or factual thing that we need to have in our indic models. So hence this example for Airavata model. Now, coming to the end of how to create an evaluation dataset or benchmark to overcome these challenges. So basically we can these are very few approaches that we can think of. The first one is collaborative translation approach, where we combine machine translation with rigorous human validation. This is already being done, but just to improve the accuracy more, we can do crowdsourcing using various platforms to involve native speakers in the translation validation process, etc. Standardized guidelines, so develop some standardized guidelines for translation to maintain the consistency across different languages and tasks. Use contextual embeddings to maintain the context and meaning of the sentences. Prompting, so carefully design the prompts to ensure that they are suitable for multiple languages. Bias mitigation, conduct regular bias audits on translated datasets to identify and mitigate the potential biases that can occur, and resource optimization that is happening because of the translations. So yeah, this is it. Thank you. Any questions?
I have a question on your MMLU part. Can you go back to that slide where you were talking about the drawbacks or the uh, things that went wrong with MMLU valuations?
Yeah.
Yeah, right. Can you double click on why were these issues, and was it because of how the data sets were formed for MMLU? Like why was it happening essentially?
Okay. So as you can see here, the first one is the default style, like where ABCD is the basic options, and the models are just evaluating on those. Now there were three variations done in this. The first one is instead of ABCD, some random symbols were given, and then the model was asked to predict the answer. The other one is where the options were changed, like instead of the regular, there was some change, like maybe A was on C or C was on A, and the last one is close prompt where options were not given. So, what this paper emphasizes is where even some minute changes, such as this order of questions or the method of answer selection, they affect the performance. So, this is basically because medium or small size models struggle with handling these perturbations. So, what we can infer from this is rather than genuine understanding, this they rely on other specific patterns from the data, and hence this issue was happening.
Okay, got it. So this is also in a way the problem for the model itself, right? Like the model is not able to generalize. Instead, it is learning patterns and then using those patterns, it might be giving the right or the wrong answer. Like how if you are just shuffling the options, basically the answer or the quality of the response would change, right?
Yes, so basically it's not comprehending the material, but rather just exploiting the biases in the data and learning the patterns.
Okay, got it. And is there any way to mitigate this? Like when we are creating, say, for example, our own benchmark, uh, any way to mitigate this? And is this only applicable with, say, like MCQ based evaluations or maybe even something else as well?
No, this was applicable with this part also, where we have a close prompt, like where we don't give any options to the model and directly ask the answer. So even then, we saw that there was a change in the rankings, and maybe possible solutions can be try more variations. Like in this itself, as we can see, there are 4 different variations, and there are different results for it. So while doing the benchmark only, if we this were not included in the benchmark. This is other paper which showed the issues with MMLU. So while including all these variations in the benchmark only, maybe that can help for a proper leaderboard.
Oh,
Maybe
got
while
it. Like have
doing the training, we can introduce these perturbations into the training data itself. So
Yeah,
that,
then the model will learn accordingly.
because we
even
see
at
that
the
model size, you see, the bigger model size is performing well in most of the things, and mid-size models, they are like randomly in one task, like the shuffling task, maybe 6 billion word is performing higher, but unknown symbols or close prompt answers, they are not performing that well. So some research into this might be possible.
Yeah, even giving combinations at the evaluation, like what Aditi is saying. So have these combinations within the evaluation framework
Yeah.
itself, and then like at the benchmarking time, you will be able to know if the model is just getting it a hit like randomly
Yeah,
or is it actually generalizing. Yeah.
right.
Aditi, did you also go through some of these efforts which like couple of startups are doing where they are translating all these English language benchmarks into Indian languages and then they are creating like so say for example MMLU has been translated to Indian languages. Arc Easy Arc Challenge has been translated to Indian languages. Have you seen those efforts as well?
So here, this part which I was mentioning, this data sets, they are the translation from English languages to Indian languages only. That's how this were created. And for
But
India,
these are as far as I know, like for example, like these data sets are pre-training data sets, like right, like they are
No,
not evaluation data sets.
no. Indic Glue is, I think, a benchmark dataset, and Sangra is a training dataset. Training data.
It's a monolingual corpus.
And this IndicGlue is the evaluation one, and this was done majorly on the translations, and hence there was this the I mentioned just a second. There were
Hmm.
some misinterpretations in the translations. So
Hmm.
that was from IndicGlue, and this Indic Extreme did not try that much translations, and even if there were translations, human annotations were present at most of the time to verify those.
Okay. I think it would be interesting, like because these are entirely new. Again, what is not clear to me is, for example, Indic Glue. If these are translation-based data sets, what is the source data? What have they translated
I
the
think
data from? Is it like these existing?
Blue benchmark was the source, I think. Right, Aditi?
No, Glue was translations from various languages. Indic Extreme was source and human annotations.
Yeah, so Glue, like Indic Glue, was it translation from the Glue benchmark itself?
No, it was a
No?
translation from Glue benchmark.
Gotcha.
There
Okay.
is, yeah.
Go ahead. Go ahead.
1 second. I don't recollect the name, but there was this one more model which translated the alpaca English data sets into around 22 languages. Uh, just 1 second. Navrasa 2.0. So this translated all this data sets into Indian languages, but it was not like benchmarks I couldn't find for this.
Okay.
Well, I think fine-tuning data set, basically. Okay, so one question, Aditi. So in the Sangraha corpus slide that you showed, okay, so verified, synthetic, and unverified. So this the synthetic portion. What is the difference between the synthetic and the unverified portion?
So the synthetic part is the translations part
Yeah.
from English to whatever languages, and the unverified is basically like all these translations were verified. Sangra verified is manually created. Synthetic was also human annotated, like, but the unverified part, these translations are not verified by human annotators.
So that I got. So like, for example, let's say Sangra synthetic is like machine translation, generation from matlab generated from machine translated data. Now verifying those is it divided into the Sangra verified? I mean, is Sangra
No, no.
synthetic is the
No,
yeah.
no, Siddhant, how it is that Sangra verified and unverified, these are scrappings from the internet itself. The difference between verified and the unverified one, so these are not converted or translated data sets, the verified and the unverified one. These are the ones where they have scrapped the data. In the verified one, they have actually verified the source of the data, that whether the source is in Hindi, Gujarati, Marathi, all these Indian languages, they have verified it, and then they have scrapped the data. So they for sure know that the language that they are scrapping is the language whatever they have verified.
They also
The unverified one is kind of like detected automatically whether the language is English or like Hindi or whatever. But these two data sets, verified and unverified, are not translated ones. These are pure internet scrap data. The synthetic one is where they have actually taken Wikipedia English, the same thing that we also did, and then translated it to I think 22 Indian languages using the same model, Transindic 2.
Got it.
in the verified part, they have also filtered out the noise and poor translations manually, which was the issue in Samanandar.
Okay, it is like human in the loop kind of system.
Yeah, so verified one would be much more clean, but from the internet source, unverified would be a little bit less clean. But again, from the internet source, synthetic is purely synthetic data translated one.
Okay.
But again, these are not benchmarking data sets. These are for
Training, yeah.
pre-training.
Training.
Yeah.
पासपोर्ट काढला 11 महिन्याची पुढच्या महिन्यात
Was someone saying something?
No, I think okay, great presentation. Aditi. Thanks. Any other
Yeah.
questions, anyone? I think not. So, yeah, we can conclude this. Okay.
Yeah. Thanks a lot, Aditi.
Thanks a lot, Aditi. Uh,
Hello everyone. So last time we had discussed that what can be the challenges when we translate certain benchmarks from English to Indic languages. So let's just quickly recap that. The first one is the cross-lingual contamination. So now what happens is even if the multilingual version of a benchmark is not contaminated, the original English version might be. So models can use the knowledge of English benchmark through cross-lingual transfer and making the multilingual benchmark indirectly contaminated. This one is one of the major issues. The second one, which we have discussed a lot in detail, loss of cultural and linguistic nuances. So, direct translations of benchmarks created in English and in a Western context often lose crucial cultural nuances. And this can be an issue. And the last one is unsuitability of standard metrics. So, what happens is standard metrics used in any benchmarks, such as the exact match and word overlap, are not suitable for Indian languages due to the non standard spellings. This can unfairly penalize a model for using slightly different spellings than those in the benchmark's reference data. And this might be an issue. So, all of these three issues were solved by Pariksha. Pariksha is a platform. Indian benchmarking is highly it helps to benchmark Indian languages very nicely. And let me go through the methodology of this. So the first point is curating evaluation prompts. So a diverse set of evaluation prompts is curated with the help of native speakers to ensure cultural and linguistic relevance. And then these prompts are passed to the models. So generating model responses to the curated prompts are generated from the models under consideration, capturing a wide range of behaviors and outputs. Now the main part here is the evaluation settings. So these responses are evaluated in two settings. The first one is the individual evaluation, where each response is evaluated on its own based on certain metrics that we are going to see ahead. And when there is a pairwise comparison, where responses are compared against each other to determine which one is better. So the responses from two models will be compared. And then constructing leaderboards, like scores from these evaluations are used to construct the leaderboards. Evaluations are carried out in two ways. One is the human evaluation, which is carried out by a company named Karya, where they have native language speakers, and the other one is the LLM evaluation, where LLMs themselves evaluate the model. In the left side, you can see a figure where the two versions of this pariksha are shown: the pilot version and the round one version. This pilot version was completed in March 2024, I guess, and the round one is May 2024. Now, there were various number of prompts. For the pilot version, there were 20 generic prompts and there were 10 cultural prompts for each of these languages. And in round one, the languages were increased, like Marathi, Punjabi, Gujarati, Odia, and Bengali were also added. And these are the total number of prompts on which it was evaluated. Moving ahead, now how does this evaluation take place? So something known as the elo rating system is used. It is widely used in competitive games like chess, where it measures the relative skills and levels of these players. So in our pariksha benchmark, we adapt the elo rating system to evaluate and compare the performance of these AI models based on the responses to these prompts. Now, this allows the system to convert human preferences into elo ratings and predicting the win rates between these models. So the first step is the expected score calculation. This formula, what does it do is it calculates the expected score for model A when compared to model B. Here RA and RB are the current ratings of model A and B, and this expected score represents the probability of model A winning against model B. So this is the first formula. The second one is, just a second. Yeah, so this one is the first formula. The second one is the rating update formula. Now, what happens is we have the expected scores and winning probabilities, and now we want to do the rating updates. So, this updates the rating of model A after a comparison, and RA dash is the new rating. Here, K is a factor that determines the sensitivity of this rating system. Now, see, SA is the actual score, which will be 1 for a win, 0.5 for a draw, and 0 for a loss. And EA is the expected one, which we calculated from here, and the ratings are updated based on the differences between this. So now the last point is the Bradley Terry model. So what happens? It is used to estimate the log likelihood of the underlying elo, where Pi and Pj are the performance parameters of model I and J respectively. Now, why do we use this BT model? In the elo model, the sequence of which model comes matters, but in our case this is not the situation, where because we'll calculate all the leaderboard ratings one at a time, and at that time it does not matter which model comes first or not, hence we use the BT model. This model assumes a fixed but unknown pairwise win rate and estimates the probability that model I will outperform model G. So let me quickly recap what is happening over here. The first step is the pairwise comparison. So for each prompt, responses from two models are compared. Human evaluators or an LLM decide which response is better. After getting the response, expected score calculation is happening, where using this formula, we calculate the probability of model A winning over model B. Then there is a rating update happening, that after the comparison, the actual scores determine uh, help calculate the new ratings, and updating the model A's rating based on the performance relative to the expectation. And the last one is the BT model application. It is used to estimate the fixed pairwise win rate, ensuring that the order of comparisons does not affect the ratings. The order of comparisons used to matter in ELO, but we are using the BT model, and hence this do not affect the rating. So the probability of one model outperforming another is calculated to provide a robust comparison framework. So this is how the methodology works. Moving ahead, here you can see two screenshots. So first one is the screenshot from the Karya app, which the human evaluators get. They get certain prompt response, and then they get three options, that if response of model A is better than B, if response of model B is better than A, or if both the responses are equally good or equally bad. And they have to select one option within this, and they have to also provide an audio recordings saying why they suggested the given answer. And here is the LLM part, where an LLM is asked to select which one is the better one. So these are the screenshots of both of these comparisons. Now the individual metrics. Remember last time when we were talking, I told that each model has to go under some individual metrics also. There are three metrics involved. The first one is the linguistic acceptability. It measures if the text is in correct language for a given language and grammatically correct, and it is rated on a score of 0 to 2. Now next comes task quality. It assesses if the answer is of high quality and provides useful information. Sorry. And it provides useful information. It is also rated on a score 0 to 2. And the last one is the hallucination. It checks if the answer contains true facts or untrue or made up facts, and it is rated on 0 to 1 scale. So these are the three metrics which individual evaluations happen on. And now there is something else also known as the inter-rated reliability metrics. The first one is the percentage agreement. It calculates the percentage of items on which the annotators agree, ranging from 0, that is no agreement, to 1, perfect agreement. So now for each prompt we have three annotators, like for the same language, and we have to see on how many of them all of these three agree or do not agree. So that is one important factor, ensuring no bias happens. The second one is the fleece kappa. It measures inter annotator agreement, accounting for the agreement occurring by chance or something like that. And now, as we have two evaluators, the LLM evaluator also and the human evaluator also. So this thing is used, Kendall's Chow. So it is a correlation coefficient that measures the relationship between two columns of the rank data, used to compare leaderboards obtained through various evaluation techniques. Now, if you focus on this figure, this shows the percentage agreement and fleece kappa scores for human and human LLM annotations across different languages. So, what does this figure show is that if higher agreement scores among human annotators compared to human LLM pairs suggests that while GPT-4 as an annotator performs well, human evaluators still provide more reliable and consistent evaluations, because you can see that humans evaluators are high range in most of the cases, except the Hindi one, because GPT-4 is highly trained on Hindi also. And the variation across languages could point to specific challenges in those languages, such as the syntax complexity or cultural nuances that GPT-4 might not fully grasp. Also, according to the paper, it was shown that LLMs are better picking only like LLM responses. So that might also be the case, but as we have human annotators also, so that will be balanced. Sorry. And in this left side figure, if you remember, while seeing the issues with MMLU, we had pointed out a specific issue that changing or slight perturbations in the model answers or something could lead to huge changes in the leaderboard. So Pariksha overcomes this as well. We can see that comparison of consistency with option flipping for humans and LLMs. So even if we flip the options, the models are still consistent, and hence that issue is overcome. So now what we see next is the leaderboard for human evaluation rank, which we have here, LLM evaluation rank, which we have here, and we have certain scores associated with it, the ELO scores that we were talking about. So for the Hindi language, you can see that GPTs currently are on the top of the leaderboard, because Hindi is such a language that it has vast resources available, and GPT is also trained on that. But when you go for the Malayalam language, you can see that the third position is obtained by an Indic LLM. And these are how the leaderboards are present. These are the human ranks, and these are the LLM ranks. So yeah, that's it. That's all about the Pariksha benchmark, which is highly beneficial for Indic languages. Thank you.